Hello, guys. Welcome once again. This clip goes with, in your Zoomdal text, I think it's chapter 16-ish, in the very beginning of chapter 16. And then another, are you guys sick and tired of studying equilibrium questions yet? I just about am, but we're not done yet. So anyways, this goes with the idea that some salts that we usually say are not soluble in water truthfully perhaps might dissolve a teeny weeny bit, and it's interesting but hard to imagine we can actually measure that teeny weeny bit of dissolving in what we call a solubility product constant. Here's an example. Although it's so general, it's hard to it's hard to really make sense of it. Let's say that this metal nonmetal combo called MX is a solid and it doesn't dissolve very well in the water. But truth of the matter is, if you get picky about it and try to look for teeny weeny amounts of this metal ion and the non-metal ion in the water, chances are you can probably find a little bit. When you say something never happens, it's a stretch. Black and white thinking, right? So however many metal ions, the rules are writing the equilibrium constants. I say n to the n power, m to the n power, and x to the m power. Perhaps I should have chose something different than this little m from the capital M, but there's no connection here between this and this. But anyways, yeah, pure solids and pure liquids, remember, aren't written in the expression. So yeah, there you go. It's called the solubility product, the multiplication. We're talking about this soluble or mostly insoluble salt that might dissolve a little bit. This means not too much without some examples, so let's just get to the examples. I wrote out a bunch. There's tables in the chapter, the text of your chapter, also in the back of your book that list these. We say that most carbonates don't dissolve in the water, so if I said silver carbonate is insoluble, oh, that should be an equilibrium arrow. What the? Anyways, I'll fix that before I put the PDF on. Equilibrium arrow. Silver ion, carbonate ion. One carbonate doesn't break apart. Two silvers break apart from the carbonate. But in any case, to say that none of it dissolves in water would be a stretch, because this says that this amount times this amount that does make it into the water is a small number, but still measurable. Same story for the strontium phosphate. It says I have strontium phosphate solid. Most phosphates don't dissolve in the water. Looks like strontium phosphate does a little bit. I just looked this number up. It's a small number. These numbers are so unimaginably small, but therefore it's also hard to imagine how they can measure it. A lot of times it's with conductivity and such. Not necessarily, though. So you take strontium phosphate, dissolve it, put it in a bunch of water, stir it good, let it settle, and you'll still find a little bit of this and a little bit of this. Oh, yeah. This 3 goes here, this 2 goes here. Don't forget to square it and cube it and such. Pure solids don't enter into the expression. Cobalt hydroxide. Most hydroxides don't dissolve in the water, so this is no exception. But truth of the matter is a teeny weeny bit of it. That's a small number, my goodness. We better work a problem or two. Oh, before I do that, though, let me say this. This Ksp is actually, you can write it either way. Like most equilibriums, I can write it like this, or I can turn around and write it like this. This is called my solubility product here. But what if I said I took some lead ion in the water and some bromide ion in the water and mixed them together? There's a really good chance they want to make some lead bromide. So the formation constant is actually the opposite of the inverse, the reciprocal of the solubility product constant. So yeah, I don't know if that makes any sense, but if I take this backwards, the definition is that this pure solid doesn't count, so put a 1 up there and these ions in the bottom. And looking at this, it's just the reciprocal of that term. So if this is a small number, then my formation constant for the reverse reaction will be a big number. Let's see. Oh yeah, another example. Mercury ions are really weird. This is a mercury 1+ ion, but 2 of them come together. So it's called the mercurous dimer ion, where 2 mercuries have come together to stick and they don't break up. They don't dissociate in water too well. So here's my formation constant, here's my solubility product constant, and in this section we'll mostly be dealing with KSPs because that's what we're interested in, but you could turn the whole story around backwards and say, well, let's make some mercury iodide. Mercury 1 iodide. Yeah, it's mercury 1, even though there's 2 of them, it's a 2 plus altogether, 1 plus for each mercury ion. Anyways, yeah, now let's just cut to the chase. Let's work a couple of problems out. Lithium carbonate will dissolve only to the extent, a very small amount. My solubility rules say that most first column metal ion salts dissolve, but I guess lithium carbonates are hard to get in the water. Not so much. So I know I can allow 0.07 moles per liter of this salt in the water. So one of these makes one of these, but one of these does make 2 of those. So check this out. Not only does the lithium ion concentration twice that of the carbonate ion concentration, but when I think about how to write the constants for KSP, this one's squared because of that. So this 2 rears its head right here in doubling this concentration as this stuff dissolves in the water, but also here in the writing of the constant expression and the calculation of what the constant might be. So this 2 times 0.074, 0.148 is actually squared. Sometimes I call this the double whammy. This, stupid I know, but this number is important. This number is important here, but it's also important here. So not necessarily a double whammy, but it's of extra importance because this ion is in a higher concentration than this ion, and in writing my constant, that exponent. Yeah, interesting. All right, let's try another one. Trying to be sneaky in general here. I might have just saw this problem from the book. I didn't think I wanted to assign it, so I thought I'd go through it with you. Some metal non-metal combo, 2 metal ions, 3 non-metal ions. They told me that a small amount would dissolve in a liter of water. 0.0000036 grams of this stuff. So I might have taken a whole bunch of this, dissolved, shook it and stirred it in water and let it settle, and then take off the water and try to see how much of this salt is left behind. Small amount. They also told me the molar mass of the salt. Well, from the molar mass, you might guess I'm going to have to change grams to moles. So I took this small number of grams, changed grams to moles. Nice of them to tell me this, although we could have found that out in a freezing point depression experiment or something. So anyways, this is my molar concentration, my molar solubility of this slightly soluble salt. How does that all work out? Well, let's see. Oh yeah. So if I can now, let me leave it like that. Sorry about that. So I write an expression. I write the slightly soluble salt that doesn't dissolve very well in water makes 2 metal ions and 3 non-metal ions, and so this number that described how much of this salt would fit into the water is doubled for this ion and tripled for this ion. Interesting and tricky. Then I just write out the expression for KSP. There's the metal ion, there's the non-metal ion, but remember that one's not only here, but it's also here. And this 3 is not only here, we're tripling that, but we're also cubing that. Oh my goodness. So look at that small number. The math is pretty straightforward, but the numbers are so small often, and we don't want to forget this squaring and cubing stuff. Ay, chihuahua. All right, next example. You guys have the pleasure of stopping, pausing, rewinding, printing these off and looking at them again. I hope you will. Calcium oxalate doesn't dissolve too well in water. I have a KSP here. What's the calcium ion concentration per se? Well, oh yeah, one of these makes one of these and one of these. So I went ahead and called these both X, and then X times X must be equal to this. So this times this must be equal to that. That's the definition of the equilibrium constants and KSP. So lo and behold, you end up just taking the square root of that KSP number, and it gets even a little bit larger. So I suppose 0.0069 moles of calcium oxalate will dissolve in 1 liter of water. All right, next example. What's the solubility of silver phosphate if I told you the KSP? All right, I don't know, but let me think about it. So I have the Ksp, small number, but let me go to the chemistry. I say this doesn't dissolve in the water too well, but I'm sure a little bit of this will make it into the water, and there's a 3 there, so 3 silvers also make it into the water. Well, then we proceed with the algebra. So this number was given to me, the Ksp was given to me. The silver ion amount is 3 times the phosphate ion amount, but I'm also remembering to cube that. And so 3 times 3 times 3 is 27. X cubed times x is x to the 4th. Do your fun algebra to the 4th root to get rid of x to the 4th. And I found x to be a small number, but still measurable. 0.000016 moles per liter of phosphate ion, which is also the silver phosphate ion concentration. Or sometimes you got to prepare yourself for this. They'll be really mean, and they'll ask, well, if I know how much silver phosphate or phosphate ion get into the water in moles per liter, can you change that to grams per liter, or even grams per 100 milliliters, which would be even a little fun conversion. So be aware, you might have to change grams to moles at some point. Let's just take a second and look at these. If I have a small Ksp, what does that say about the solubility of lead hydroxide as compared to calcium hydroxide? This is fairly large compared to this one. Well, here's the story. I'll tell you. Since I can't ask you, or I can ask you, but only you know if you're answering. I don't know if you're answering. Let's see. Oh, yeah. So here's the deal. The smaller the number, the less of that substance dissolves in the water, dissociates. So I say it's the least soluble, and I say the other one's the most soluble. And I can do that because it's a 1-to-2 ratio, 1-to-2, 1-to-2, 1-to-2. If it wasn't 1-to-2, I might want to watch things a little more carefully, because then I couldn't just look at the constants. And like if one of these salts was a 2-to-3 or a 1-to-3, then I'd have to do some more math with these KSPs to find out exactly how many moles per liter would fit into the water. But that's a simple comparison. A mixture contains calcium, magnesium, lead in a liter of water. As I slowly add hydroxide, if I were to slowly add OH minus to this, which ions would precipitate first? That means this doesn't dissolve in water very well. Neither does this, none of them do. But which one would start to undissolve themselves first? Start to see precipitations first. And the answer is this one, because it's the least soluble. This one would precipitate last. In other words, since this is like 1,000 times less soluble than this one, you could separate the lead hydroxide from make you a solution of magnesium and calcium, leaving the magnesium and calcium in solution, but pulling the lead hydroxide out as a solid precipitate. And that's a good way to separate ions. I am almost out of time here. Oh yeah, this is just reiterating the fact that if it's not 1-to-1, or if they're not the same stoichiometry, 2-to-3, 2-to-1, 1-to-1, you can't just take the Ksp and assume that if it's small, you know the molar solubility. You got to actually calculate it. So I actually took these from the text. But anyways, you have to calculate this to figure out exactly how it worked. Do I have time for one more example? Barely. Solubility of lead chloride into a solution. Oh, the common ion effect. Yeah. So what if this is not coming from... You know what, guys? I think I have to work this problem out on a separate video. I'm almost out of time. Yeah, thanks for watching, and I'll catch you soon.